This will be a video walkthrough of problem 1 on our problem set 1. So we're asked about this baseball pitch and we see some key numbers that will help us to solve the problem. I notice that I'm given a combination of miles per hour, maybe because culturally that'll mean something to me, 100 miles, 100.9 miles per hour. But then I'm given metric or SI units as well. The SI system of units means Système International, and it means that we're using meters, kilograms, and seconds. Our solution should include a sketch as well as equations and words. Let's see what that looks like. I am going to sketch the initial height of the pitcher and the distance that the projectile goes. And then I know that this motion is going to be parabolic, like all the projectile motion that we're studying in this problem set. What are we asked for? I see the question words here. How far would the ball fall vertically? So we want to know this, the difference between the initial height and the final height. We are told how far the ball travels. It travels from, let's say, x0 equals 0, and x final is 45 meters. We're going to use an acceleration due to gravity of 10 meters per second downward. And what we want to know, oh, this is not 45 meters. What am I saying? 18.4 meters, and the speed is 45 meters per second. So let's put our velocity, initial velocity here is horizontal, and it is 45 meters per second. So let's think about the scale of the problem first. It's traveling 45 meters per second, but only traveling 18.4 meters. So that looks like it's going to take about 18/45 of a second to travel this far. Just estimating that's about 2 nines out of 5 nines. So 2/5 are about 0.4 seconds. So we can use that to estimate how long this will take, but we can also put the actual numbers in. So let's think about time first. I want to see how long it will take to fall before I can say how far it falls. So how long it takes is how long it takes to reach home plate here. That amount of time. We have x as a function of time is the x I start at plus my x velocity times how long I've been going that fast. Is the velocity going to change along x in this problem? It is not. Once the ball leaves the pitcher's hand, the ball will continue with a constant horizontal velocity, but an increasing vertical velocity as we move along this path, and that's what's causing the path to curve downward. So we see that 18.4, the final distance in meters, equals 0 meters, the location where we start on the pitcher's mound, plus 45t. Solving this equation for t, we see that t is equal to 18.4 over 45. Let's check our units. 18.4 meters over 45 meters per second. We see that meters cancels meters, and 1 over seconds is seconds. That comes out to 0.41 seconds. And again, in this course, we're not going to be too particular about significant digits, but we'd like to be within one significant digit of the totally correct number, just to be in the reasonable ballpark. So I have 2 digits here, 3 digits here. We're going to report 2 digits on this time. Now, how far has the ball fallen? Well, I know y as a function of time is going to be the y I start at, plus my vy, initial vy velocity, times how much time has gone by, minus 1/2 gt squared. Being careful with this minus sign, I know that that force is pulling downward and there's going to be a downward acceleration. In this problem, I'm using g equals positive 10 and letting that minus sign represent the downward acceleration. So y of t represents y final, y at any time, but the time of interest here is the final time, so y final minus y0, which I could also notate as delta y, the thing we're looking for, how far this falls. This is delta y here, is going to equal vy0. Is this moving up or down as the pitch is released? According to our diagram, it is not. And are we told? Thrown horizontally, yes. So there's no vertical velocity here. That's nice because this term is 0. So the distance that this falls is just 1/2 gt squared. You might wonder, why is there a minus sign here? It's because our delta y is negative, because the ball's falling. So delta y equals negative, g is 10 meters per second squared. So this is negative 5 meters per second squared, 1/2 of 10, times the number of seconds squared. We saw from our first part here that the number of seconds is 0.41 seconds, and we square that. Notice that the squared seconds in the denominator and these squared seconds in the numerator cancel to give us the units we expect, which are meters, and that comes out to a delta y of negative 0.84 meters, which seems not unreasonable. for a distance for that to fall, that's maybe about a little less than half of a body height. So that is a solution to problem 1. We've checked our units, we've checked the reasonableness of the magnitude of the solution, and we've shown our work throughout.